Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support power system operators across the 5 action pillars. Foundation of the GPST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. ESIG is the lead on Pillar 1, and more information on the GPST can be found at www.globalpst.org. As the lead on Pillar 1, ESIG would like to welcome you to the first webinar of our 2022 monthly Join to GPST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and focuses on the GPST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both the founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and academia participating in the activities of the Research Agenda Group and the Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the GPST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about GPST and how to engage, please go to www.globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I'd like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we'll use the Slido platform at slido.com. You need to open a browser window, go to slido.com and enter ESIG25 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save around 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today our webinar is on the topic of managing grid stability in a high IBR network. Based on the number of registrations today, it looks like it's going to be a blockbuster. The interest around the world in the stability of power system networks with a high share of inverter-based resources and more with grid-forming inverters is simply overwhelming. Today's webinar will feature Julian Leslie, Chief Engineer for the National Grid Electric System Operator in Great Britain. Julian is responsible for preparing Great Britain's electricity network for net zero operation, defining future network needs so that market participants and network owners can invest in the right technology solutions at the right time. He's also responsible for the transmission system interconnection process. Julian represents National Grid ESO on the GPST Research Agenda Group, or RAG. NGESO is one of the 6 founding system operators of the GPST and a member of ESIG. Julian is active in the work of the GPST and in setting the research agenda through the RAG. I've been on many calls with him wrapping up at close to midnight his time. I can tell you he's one very dedicated person, and I feel very fortunate to have him here with us today. The webinar today will focus on the operation of the GB electricity system, demonstrating what it really means to operate a low-carbon network. It will address what actions and changes National Grid ESO is taking to ensure a safe and stable grid. The presentation will use a case study of system oscillations experienced last summer, focusing on what has been done to mitigate the risk, identify the root cause of the oscillations, and create long-term solutions. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG25 to ask your questions. And without any further ado, let's go ahead and get started. Julian, I'll now turn it over to you.
Right. Thank you, Charlie. Thank you for that great introduction. And good evening, good morning, wherever you are in the world listening into this call. It's a great pleasure to be here and to share some of the activities that we're doing here in Great Britain to make sure that we can operate a high penetration of IBR or low carbon power grid. What I want to do this evening is just walk you through, as Charlie said, some of the work that we're doing, some of our ambitions and where we need to get to it and the sort of timescales we need to get there. What we're seeing across the British network as we get these low carbon days and high wind output, as we say, looking at the Scottish position in particular from last summer, and then really what are our ongoing initiatives to make sure that we can deal with this ever decarbonising grid system that we are very fortunate to have here in the UK and supported very strongly by very clear and strong government ambitions and targets. So first of all, in 2019, when the electricity system operator here in GB became separate from the transmission owner, we set out with a very ambitious ambition that we would be able to operate the grid system carbon-free by 2025, which at the time seemed like 5 years away and we had plenty of time to do it. Now we're only 3 years away and the time is running out. However, we are in a good shape in order to meet this ambition, and much of what I will speak in the next 20 minutes or so will cover that. But what do we mean when we say we're going to operate this grid system at zero carbon in 2025? What we're saying is that when the market delivers us a totally zero carbon solution, so that would be nuclear, wind, solar, hydro, here in GB, that we as a system operator will not need to take any system or balancing actions to sort of move that market position and create carbon emissions. So as you might imagine, today when we get these very high intense wind days, we need to take actions in the grid system in order to turn off the wind to create the headroom to bring on the rotating mass in gas-fired power plant in order to create the inertia. And in 2025, that's what we are trying to avoid doing. You know, in 2025, it'll only be for a few hours on a sunny, windy August afternoon, probably. But what we need to do is then obviously build on that. We've demonstrated the capability, and then build on that as we go forward over the years. In order to do this, of course, we are very much market-led in the UK, so we're a strong believer in markets as a system operator. Our government is a strong believer that competitive forces get the best price for consumers. And therefore, we need to open up all of our systems and balancing services so that zero carbon technologies can participate in those. And also, we are driven by cost, and our license to operate says we've always got to take the least cost action first. And therefore, if our least cost action was to run a gas-fired power plant, we would have to do that at this point in time, even though we would have a zero carbon option as an alternative. And that's really good, because what that does mean that the options and the technologies that we are bringing onto the market are driving down costs for the consumers. So not only are we decarbonising the grid system, but we're also making it lower cost for consumers also. We've had huge success here in the UK over the last sort of 9 or 10 years or so, where we've decreased emissions by 65% over that period. And coal, for example, has gone from probably being 60 or 70% of our generation 10 years ago to last year it was just over 1% of our annual generation came from coal. And in October 2021, the UK government wasn't happy enough with that ambition, and it wasn't happy enough for the electricity system to sort of wait until 2050, when as a nation we need to be net zero across all energy vectors to be net zero. So the government said just ahead of COP26 that we would have a fossil fuel free electricity system by 2035. And as many of you on this call will know, 12 years in this industry is almost a blink of an eye. And yet we've got to go from a network which today ran 51% of gas on the system to this same day in 12, 13 years time, where there'll be 0% gas on the network for that period, for that day. And it's not just the day, it's the week and it's the month and the full year round process. So that is the challenge. You can see from the graph at the bottom there just the carbon intensity by year and how it's dramatically reduced over the last sort of 9 or 10 years, from the very black line in 2013 at the very top to the sort of the lighter grey and blue lines towards the bottom, which is showing even our most carbon intensive days are only a third of what they were 10 years ago. So it's been a huge success story, but these things, as you know, don't happen by accident. So there's 5 engineering challenges, only 4 in here because the other one is system restoration without fossil fuels, which we are doing lots of work on. But in terms of how you're managing that minute by minute, second by second management of the grid, we sort of bucketed up the work and the activities into 4 key areas. Frequency management, and I'll talk more about that later. Obviously, you can be less worried about frequency if you have a high inertia system, but as your inertia falls, you need to be more worried about frequency and get quicker and faster acting frequency products onto the system. Stability, again, with a more non-synchronous generation, you don't have that rotating mass. So how do you ensure that when you get a fault in the system or some disturbance, that actually the system remains stable? So short circuit infeed, inertia, understanding how those can be replaced with non-synchronous generation and other technologies has been a key piece of work. And as I say, we'll come into that very shortly. What we're not going to talk about tonight so much, though, is the last 2. Voltage management. We see a real swing in power flows, as you can imagine, from being a windy day where we have a lot of wind in Scotland, where all the demand is in the south around London. And we see big power flows on the network, which need voltage control equipment to support the bolts to manage that huge power flow. Equally, though, when we have little wind coming from Scotland, we have a massive 400,000 volt network that is just acting as a big capacitor, and therefore getting volts down overnight is becoming a real problem for us. So I'm not going to talk so much about that today, but that is something we're also managing and finding new technologies and new ways to get competition into that space. And then thermal, managing our thermal constraints. We have something called Connect and Manage here in GB, which has really enabled the UK to really accelerate its decarbonisation agenda. And Connect and Manage means that as a new generator, you can connect your generation, just making sure the very local works are completed to the nearest substation, etc. And then the wider sort of broader transmission works can wait, and they come on much later after the generation is connected. It does result in some higher constraint costs, but only for a very small percentage of the year. And what it means is the rest of the year, that wind generation is in the market, driving down wholesale energy prices, and also obviously reducing the carbon intensity of the generation on the system. So it's quite a tricky one to balance, but thermal constraint management is something we're really focusing on, but again, not really a topic for today. So moving on then, so what are we seeing in terms of today's focus, which is around high IBR systems or high non-synchronous generation penetrations on the network? And we are seeing a huge decline in inertia on the system. The 4 graphs on the screen here are each of our 4 credible scenarios looking out to the future. It doesn't matter what the CT and the leading the way really stands for, but the leading the way in the top right there is the most aggressive sort of decarbonisation of the electricity network. And you can see that for many periods in the year that we will be below our threshold, which is about 130 GVA seconds, which is what we plan to be able to operate the grid at a stable position on at this point in time. So we need to make sure that in those low periods of time where the inertia is really low, that actually we have the tools and the capability to bring the inertia back up so that we can get around that 130, 140 GVA seconds of inertia on the network. So when you combine that with also the short circuit level, which, as you know, is really important in terms of that grid stability and ensuring that the protection systems on the network can function correctly and we can clear faults cleanly and safely from the grid. You can see that as we decarbonise the grid system across GB, the very southwest at the bottom there with Devon and Cornwall is a very rural area with lots of solar and smaller wind. But you can see at the very north of the country, Scotland, which has pushed really hard to get renewable generation on over the last 10 years. And they now have there's about a 4.5 gigawatt peak demand in Scotland, and they have over 12 gigawatts of wind installed. So one of our big problems is transferring that wind from Scotland to the rest of the nation. But as you can see in those periods of time, and as you would imagine, the inertia and short circuit infeed in the Scottish region is very, very low. But you can see from the maps of GB at the bottom there, it declines massively, not just in Scotland, but as we get out to 2030, we have very low short circuit level infeeds pretty much across all of Great Britain. So this isn't something we can just sit back and watch and see what happens. We need to take proactive action to manage that. Because as a result, what we saw last summer in Scotland was a bit of a result of the high penetration of IBR, very low synchronous generation actually in Scotland, although the inertia across GB as a whole wasn't anywhere near the lower limits. It's just that Scotland, being in the very north, was sort of on a not quite so integrated with the rest of the system. And we saw some quite severe voltage oscillations on the network, which seemed to be about 30 minutes apart and lasted for 20-25 seconds. And these oscillations had a frequency of about 8 hertz. And I think there are about 14 kilovolts as well in terms of the magnitude. Well, actually, the graph shows a bit higher than that, 30, plus or minus 30 kilovolts from the sort of where it was at the starting point. So that's quite an interesting phenomenon to be in the control room and to see this happen. And we've spent a lot of time over the last months trying to understand what was going on in the network, what caused these disturbances in the first place, and then how we can get actions in place in order to manage those. It did have a wide impact across the network, and some of our connected generation saw these oscillations and their protection tripped them off the system in the correct way. So it's a really important issue that we need to understand, not only from a sort of a nationwide sort of grid stability issue, but also from that local perspective and ensuring that we're not damaging people's equipment and allowing generators to trip off the system. So initially, obviously, we weren't sure what the root cause was. So we took some very short-term actions and we gave advice into the control room just to run a bit more rotating plant. There are some hydro machines in Scotland that were off for maintenance at the time. So as they have come back, we've sort of said, look, if there's 5 or 6 of these machines, we need to be running 3 out of the 6 to make that happen. So that is running, and we've done that since August, and that sort of seems to have calmed the network down. We've not seen the oscillations since. However, that is a bit of a sticking plaster. We really need to understand what was the root cause of the issue in this part of the network. So we've been working with our transmission colleagues in SSE at the very, very north of Scotland, and also Scottish Power in the middle part of Scotland, along with ourselves, and collating data and getting our best people to really understand what is going on. What we've had to do is build this very detailed EMT model of the supergrid network in the north of Scotland. We didn't have that before. We used a Power Factory Silent product, which is great for your sort of steady state analysis, but doesn't really give you the level of detail that you need when you're looking at these dynamic sort of millisecond by millisecond performance of the grid. So we're building that model, we're getting data, we need more data from generators that may or may not be sort of detailed in the grid code, so we're sort of trying to work through that and the confidentiality of getting all of that information. What it has done though, is that it has highlighted that there are some gaps in the grid code and the data requirements that we need from generators and other dynamic devices connected to the grid system. So that's something that as we move forward and we do get more of these low carbon grids across the world, then I think everybody looking at their sort of data requirements and making sure that as system operators, we have access to that so we can really model the system and understand what is happening. And data, the key thing in all of this is data. And really, really, as you can imagine, really, really granular data as well, using PMUs with millisecond by millisecond data, looking at all the alarms and SCADA systems, not only from the TOs, but also what the generation is using, looking at the network configuration of these very large offshore wind farms and just making sure there's nothing untoward going on between how they were configured at that particular moment in time. Was there any plant that was in service or out of service that there was a change? And really, was there anything that we can pinpoint to those half-hourly sort of oscillations that was really triggering the oscillation to happen? So we're still going through this huge amount of data, so we haven't yet got to the root cause of the problem. As I say, we are comfortable that the actions we've taken have mitigated the effect for now, but we are really getting on and really trying to delve deeply into the data, into the analysis, building the models, so we can try and replicate the situation that happened on the day, so that we can really get to that root cause, so we can understand it much better. Luckily for us, we sort of knew that some of this stuff was coming, so we had some innovation projects running, which was helping us to better understand this EMT environment. What the oscillation situation did in Scotland last year is just really accelerated this work and really proven that our innovation projects are absolutely the right projects to be doing, and trying to learn as best we can using academia and other suppliers in the market to work alongside us to really understand and get into the detail of this EMT modelling. So there's some links there, which I'm sure we'll be showing the slides later, which you can follow and get more information about what those innovation projects are all about. So that's a very much a case-specific issue that we saw in Scotland that we're looking to manage and mitigate. But looking more broadly across the whole of GB, looking at this low inertia system out to 2025 and then to zero carbon 24/7, 365 by 2035, what other actions and activities are we doing to ensure that we have a safe and secure grid going forward? I mean, the first thing we've done is that we've introduced the world's first real-time inertia measurement system. And here's a picture of it. It's just a nice shipping container, but in that shipping container, there's a super capacitor, one of the largest in the world, a 10 MVA super capacitor, with some very smart power electronics. And what this thing does, it pulses onto the network every few seconds, and then there's PMUs around the network that then measure the impact of that pulse. And by measuring those two things in real time, doing the correlation, looking at the impact, then there's a calculation that can be made to assess the real-time inertia on the grid system. Once we have that, and once we build up some knowledge, then we'll be able to use that data to be able to forecast where the inertia is going. And also, we've worked with GE, who's the supplier of our real-time network system management tool, and they're also doing an online assessor also, so using the data, using the output, the generation patterns, etc., to do a calculated inertia also. So we're going to have the two things. We're going to have the real-time inertia from this box you can see on the screen. We're going to have then the calculated inertia from the GE system, and by comparing the two and being able to forecast and really hone and fine-tune the calculations. So we've been really confident where we are with regards to inertia on the system, and then take the appropriate actions to increase, if necessary, that inertia to ensure a stable system. So that is a world's first. I know Reactive Technologies are talking to other system operators around the world, but this is the first one that's been commissioned and installed here in GB. So once you can measure your inertia, it's then, well, what do you do with that? And what other products and services do you need on the grid system? So as I said at the top of the presentation, as I'm sure everyone on this call pretty much understands, that you've got a huge trade-off and balance between faster and more frequency response or more inertia. And a real challenge when you're trying to find that economic solution is what is the right break point? Do you go really, really low on inertia, but lots of really, really fast frequency management? Or do you go very, very high on inertia and then less and slower frequency management products? So we've tried to define sort of the key sort of trade-off point for us here in GB. And last October, so about 15 months ago, we introduced something called dynamic containment. So this is a very fast frequency response product that's monitoring the frequency all of the time. And what it does is that when we have a fault in the system and the frequency falls rapidly, then this service delivers very quickly, and it can deliver the full capability. So if it's a 50 megawatt battery, it can deliver a full 50 megawatts within that first second. So as you imagine, as the inertia is falling on the system, the inertia is fallen, the frequency is falling, then we've got about 1,000 megawatts of this really, really fast frequency response now. So we get 1,000 megawatts injected into the network within a second, which then arrests the fall in frequency. Then our other frequency response products kick in and then return the frequency to the operating standards. So that dynamic containment has been a huge success and is now allowing us to operate the grid in a way that I never thought possible even sort of 18 months ago. Because it acts so quickly, you can run the system at very, very low inertia levels. However, even once we've got all of this, we still need to find other sources of inertia and short circuit infeed. So what we've done is we're running these things called stability pathfinders. So they're called pathfinders because it's very much a trial by doing process. We haven't sat in a room and worked out all of the market and commercial and sort of technical issues. We sort of learned as we've gone along, and we've tried, as I say, trialing by doing, which has meant we have been able to get products to market very, very quickly, but at the same time having the checks and balances and assurance that they are going to do what we say they're going to do. So phase one stability pathfinder, which was very quick turnaround. We contracted in January 2020, so just 2 years ago, and already most of the machines we contracted for are on the network. And these machines in phase one were either a pump storage plant that is just spinning their turbines in air or in water and providing that inertia, but it's a dedicated unit for inertia and short circuit infeed. We have a gas-fired power station that has converted itself to be a rotating synchronized motor, effectively, again providing inertia and short circuit infeed, which is really great, sort of repurposing an existing asset. It's a pretty low cost to do that. We've also got 2 GE purpose-built machines, and their sole purpose was to meet the needs of this contract. So these are quite compact rotating machines, and they are as heavy as you could possibly make them. So each one weighs 200 tons, and they rotate and they synchronize with the grid, and they sit there 24/7, 365, providing short circuit infeed and inertia. And it's taken us 18 months really to get from contract award to the things on site, and then the final one of those 2 machines commissioned last Friday. So we bought in phase one 12 GVA seconds. As I said earlier, we need about 130 overall on the grid system. So nearly 10%, but that's 5 to 8 machines equivalent gas units or coal units. At 320 million, we think that's going to save the consumer about 130 million over that 6 years by doing that. We've got 2 other phases running, which are going to be much bigger. So phase 2, we're about to announce the tender results in March of this year. We think that's going to be in the region of 500 to 600 million pounds, and that's going to be for 10 years, just focused in Scotland, very much with a short circuit infeed as a priority, but obviously with that comes inertia. And then phase 3 was launched just before Christmas, which is a nationwide or GB-wide inertia product. And again, we'll be buying much, much more in that, and that could be 600, 700, 800 million pounds worth of contracts again over 10 years. Each of these, though, we will only go ahead if it saves the consumers money. And from what we can see so far, it will save the consumers tens of millions, if not hundreds of millions of pounds over those contract periods. So that's what we're doing in terms of new products and services. To support all of this, though, and to really look to the future and to break this sort of chicken and egg solution problem that we have, that developers don't really know what the system operators need, and the system operator doesn't really know what the developers can deliver. So we spent a lot of time modifying our grid code to provide a minimum non-mandatory specification to define what capabilities of the grid forming capability on inverters could be. So this has been in development for quite a number of months and years, with many, many working groups and many, many people across the entire industry contributing and working together. Now this grid code modification, which went live just a month or so ago, now really details at a technical level what it is as a system operator, as a minimum, what performance we need from a grid forming inverter. And that's what this grid code was all about. Much more information on this online. There'll be a link at the end of the presentation which you can follow up on it and get into the detail of what that really means and how we got to that conclusion. But from our perspective, what it allows the market to do now is that when they're building an inverter-based product, they can look at the requirements, and actually they can look at our future inertia requirements on the network. They can look at the size of the markets I've just spoken about and say, actually, for a relatively small additional cost now, I can put in this grid forming inverter, and that means I can participate in those markets into the future. And then this way, as a system operator, we will have a mix of renewable generation with grid forming inverters, which would be great, combined with some of the devices and technology I've just been talking about, which is still physically rotating. And I think that mix of technologies across the system is going to give us the confidence and the resilience that we need in order to operate a zero carbon grid. The other thing we're thinking about as well is that with frequency and voltage and thermal ratings, our grid codes or security and core supply standards, it's very clear to define what the range of operation should be. Therefore, as a developer connecting to a grid, you know that your target volts has got to be 400 kV plus or minus 10% or whatever it is, that your frequency management needs to follow this droop curve or whatever it might be. But for short circuit infeed, there isn't such a thing. So we're working hard now to understand, well, how can we define the short circuit levels on the grid? Do we as a system operator need to say, look, there will always be this minimum level of short circuit infeed across the grid, and we will buy products like I've just been talking about in order to maintain that in every corner of the grid? Or do we say to the developers that we're connecting to the grid system, you need to have devices on your development that allow you to operate at these hugely low short circuit infeed levels? And that's what we're just working through now, is understanding what that right solution is, how you get there, and how you ensure pre-fault that actually if the fault were to happen, that enough short circuit infeed would be available on the network. It's such that it's stable and that the protection systems and everything else work as they should work. So it's a really interesting piece of work. And I said to my team initially, I said, well, we just need like voltage. Surely we just put a range in there and we guarantee as a system operator we're good to go. However, my team tells me it's not quite as straightforward as that. So there's more work to go on that. But I would expect in the next 6 months or so that we'd have cracked whatever this is, and we'll be able to define what it is and how we're going to manage short circuit infeed and give our customers, the developers connecting to our grid system, a very clear articulation as to what it is their devices need to operate within. So that was all I really wanted to talk about this evening. So you can see all the links there, which will be on the slide deck as we circulate after today's conversation. So please feel free to follow the links. There's a whole host of information, the technical assessment, the commercial assessment we're doing, FAQs on the process, and all that information is there to be looked at and to understood. There's also dot boxes and all of those. If you do have questions, you can fire them into there. Or obviously, if you do have any questions, we'll take some in a moment. But also, you know who I am, so you can contact me directly, and we'll do what we can to help explain what's going on, to help you all understand it. So I think that's a very whistle-stop tour to a huge amount of work that we as the electricity system operator here in GB are undertaking. And as part of the GPST, it's great to share this information and to learn from the other 5 founding system operators, and to share this knowledge with our colleagues in Australia, California, Ireland, Denmark, and I'm sure there's somewhere else that I've just forgotten, ERCOT in Texas. So hopefully you found the session interesting, and I look forward to answering your questions. But with that, I will hand back to Charlie.
Okay, thank you so much, Julian. That was quite a whirlwind tour. Appreciate that. We've got a lot of questions that came in through Slido, And before we get into them specifically, I just want to follow up on that chicken and egg problem that you mentioned. I think that's a very fascinating problem. I think it's something that operators around the world are dealing with, is how to break that vicious cycle of the system requirements, the equipment capabilities, and the grid codes. It's like a circle, and how do you get into that circle and start getting the products and services that you need for the future? So you've done a masterful job, I think, of cracking that nut. And one part of the nut I want to explore just a little bit before we get into more detail on the questions is the grid code modifications part. You talked about GC0137 modifications, which you can get a link to and go dig into in more detail. But are those envisioned to be a progressive set of modifications that you will slowly evolve over time as you get more experience with what you've already done, or you feel like you're most of the way there with that? How are you looking at the grid code part of the chicken and egg situation?
Yeah, I mean, our first priority was to get the industry together to look at what is capable and what the inverters are capable of doing, and then trying to match that to actually, well, what it is do we need. So we sort of, as you say, we sort of cracked that process. This is a minimum standard that's in the grid code. So we're saying, look, as a minimum, to get anywhere close, your grid forming inverter has to perform in these levels. What we hope to do, and what we hope the market will also see, though, is we publish more and more information about how it is we're going to manage and monitor short circuit in-feed levels, where the inertia levels are going, and the inertia products that we bring to market. That actually people will be able to say, well, actually, I'm not bothered about the minimum standard anymore, because actually I want to contribute much more in short circuit in-feed current or whatever it might be, because there's a bigger market value. Obviously, if we learn as we go along and we go, actually, some of this isn't working, or we need to define another parameter or whatever, obviously we can amend the grid code. But I think our proposition is this is the minimum standard, and it'll be because of the transparency in our markets and the value in our markets that actually developers will start to look at, okay, we can meet the minimum, but actually I'm going to give you more in these sort of characteristics that help you manage the grid, and they'll get paid then to the markets to do that.
That's a very nice linkage between the codes and the compensation in the markets. I think you've really done a great job in cracking that nut. So here's almost a follow-up question, I guess, from Dimitri at BPA. Do you require new inverter-based resources to be grid forming to achieve the decarbonization goals?
I mean, that's a great question. Obviously, we've got what have we got? We've got about 27 gigawatts of renewables on the network, plus the embedded generations. We've already got 35 gigawatts of renewable inverter-based generation on the system so far. We've operated the grid at 88% zero carbon, which includes nuclear and hydro. So we are fortunate in GB that we don't need to be 100% IBR, because we have existing nuclear. We've got a new nuclear program with Hinkley Point C coming along. Plus we do have bits of hydro and also pumped hydro around the network. So I think we are in that fortunate position. So with the pathfinders, I was just talking about getting some of the sync comps and the special machines that GE have developed, the converted CCGT plant, just to provide that inertia and short circuit in-feed. I think that means then that the existing renewable generation doesn't need to then change to grid forming. And I think that the market value is so great. Now we've set the minimum standard. I think that as new developers come to market, that's going to be one of their key questions. How can they increase their revenue streams? And actually putting a grid forming inverter in place could be one of those ways that they would increase their revenue stream. So I think that's where we are. I mean, it'd be great if we can get more and more of this stuff, because it will help overall, but not everything needs to have one.
So you've put a very interesting market mechanism in place to let people make their own decisions.
Yeah, and then we as a system operator, we can monitor that and manage that. And if there's a shortfall, we run a market, which then gives a market signal, and we either buy something like we're doing currently, or that will encourage them to put a grid forming inverter in.
Right, very clever. Okay, here's one on inertia. I think you've answered part of it. How do you measure the system inertia, the overall inertia? But the second part, does it matter where the inertia is located?
So yes. So that picture I showed you, that's in the northeast of England, which is sort of electrically towards the middle of the network, I guess. And as I say, that pulses this 10 MVA supercharged capacitor into the network. And then we've got some very specialized PMUs around the network. And obviously they all get a slightly different reading. So we calculate inertia on a regional basis. And that is what's driving things like the phase 2 of the Pathfinder. Yes, it's a short circuit in-feed driver primarily, but it's also, that is where we need that locational inertia also. And then as we look to England and Wales, even the phase 3, that has a locational element to that tender process, just to ensure we have enough of rotating mass around the system. And once we get to those regional levels, then we think there'll be a bit of a shortfall still. Then we can just add more inertia than comes anywhere across the system. So yes, inertia is regional, and it is important that you get it in the right locations to manage the entire grid and to keep it all stable. Okay,
next question related to inertia also. What event is used to determine the national minimum inertia requirement? And is it your biggest loss of generation or something else?
Yeah, no, so it's our biggest loss of generation, but combined with the protection settings as well. So we've just changed 50,000 protection settings on embedded generation, so to remove it from quite a sensitive rock-off relay setting to one which is less sensitive. So now we've increased the rate of change of frequency that we can withstand on the network before the generation trips. So looking at your largest loss, looking at what happens when the frequency falls and do you lose any more generation, that was what was setting the inertia levels. Now it's just our largest loss because we've pretty much changed all of the embedded generation loss of mains protection.
Okay. And I guess this question really is asking whether you can say any more about the what triggered the oscillations in Scotland.
It's a great question, and I wish I knew the answer. I thought we'd know by now. The teams are still investigating it. We've got some suspicions and some ideas that we're sort of tracing down. As I said earlier, the challenge here is that historically we've not had this level of granular detail that we can do this EMT study from. So even though we have our suspicions, what we're now trying to do is get the data, build the models, and then test our suspicions as to what it might be. So yeah, so I'm hoping in the next few months that we'll be able to sort of draw that study to a conclusion and really identify what the root cause was. But as I say, we've got the sticking plasters in place. We haven't seen the oscillations since, and we've had our lowest carbon day since then. Our lowest carbon day was just after New Year on that Sunday at 88% zero carbon.
We'll have to stay tuned for further information.
Yeah, absolutely.
Okay, this next question's on short circuit strength, and I saw another question down below related, and I think you talked about it a bit. How will you increase the short circuit strength during the high VRE production, only with synchronous compensators, or, and the related question was, what are you going to do about loads that require very high short circuit strength, like arc furnaces? How are they going to be managed as you make the transition to inverter-based resources?
It's a really good question. So yeah, so the short circuit system strength, obviously rotating plant is great for that, so synchronous compensators or these other devices that I've spoken about, but also the grid forming inverters also, if you put in the high enough rated piece of kit, then obviously that can provide quite a bit of short circuit in feed also. The load element of short circuit is an interesting one because they also need to decarbonize, and they're sort of coming up with weird and wacky ways as to how they might do that. That's why short circuit in feed is really, really locationally specific. So inertia is regionally specific, but what we're finding is short circuit is even smaller than a region. So you've got to get really specific with the individual sort of load and characteristics of that load. So yeah, so we need to factor all of this stuff in. Luckily, where our arc furnaces are currently, there's a high short circuit in feed, so we haven't had to tackle that problem yet. But it will come, that's for sure.
It will come. If you build it, they will come. So, kind of an engineering question on negative sequence current. How big a problem is the absence of negative sequence current from IBR in terms of protection engineering?
I'm going to have to take that question away, Charlie. That's the level of detail, I'm afraid I don't know.
Okay, we'll get back to that in the Q&A and the follow-up. Maybe this next question is maybe a little too detailed also, but when measuring system inertia, does synthetic inertia contribute towards the measured inertia or only the actual rotating machines?
That is a fantastic question, which I will ask Reactive Technologies tomorrow.
Okay, no problem. Another question going back to the event in Scotland during the voltage oscillation. Did any IBRs trip, or how much of that trip, do you know? I think you had mentioned that you lost some load.
Yeah, so it wasn't that many. It wasn't all inverter-based connected generation for sure. It was just a couple. And as I say, that's part of the investigation. What was it about their particular setup, their particular protection arrangements that saw these oscillations and sort of took the action that they did? Because as I say, not all of them did in that same locality. So that is one of the things that we're trying to understand as to why those wind farms did take that action that they did when they saw the oscillations. But it wasn't many, that's for sure.
Okay. A few more related questions. So I'm going to skip down a little bit.
Yeah.
To the modeling that you're doing. I think there are a couple of questions about the EMT models. Can you say anything about the environment in which they're going to be built?
No.
No.
I'll have to say that one away as well.
We'll
I mean, Charlie, as I said to you, I haven't said to the group actually, I was, one of my technical colleagues was going to join me tonight, but unfortunately he's been struck by COVID and is not very well, so was unable to call, and he would have been able to answer some of these questions. So apologies for that. But Charlie, I'll follow up afterwards and answer these questions.
Yeah, no problem. Question on dynamic containment that maybe you're familiar with that. On the difference, it said that they noticed that ERCOT's fast frequency response product is a 1/4 second response time. And it doesn't say how much of response is available at that time. I don't know if it's 80% or 100% or what, but any idea of how your 1 second response time for dynamic containment compares to that, why it's different?
Yeah, so I did ask Julia of that, because if you might remember, Charlie, I was on a call going, great news, we've got this product that delivers in a second, and Julia said, oh, but ours delivers in a 1/4 of a second. And the difference is that ours is dynamic. So ours will proportionally deliver what is required in order to arrest the fall in frequency. So if it's a small disturbance, if it's a 50 megawatt battery, it might only put 20 megawatts in. If it's a large disturbance, it'll deliver the full 50 megawatts in the second. Whereas I understand, I think from ERCOT, if it sees a frequency, it just delivers the whole lot in a single hit. It's not dynamic. It doesn't understand what's going on. It just says, oh, it's triggered. I'm just going to deliver my 50 megawatts. Whereas a dynamic containment, that's the clue in the name, I guess, is dynamically monitoring and managing and delivering the response that it needs to deliver, depending on the size of the shift.
Okay. Question here about the 50,000 settings that had to be changed in a short period of time. I think the question is, how did you manage to change 50,000 settings?
So we used the distribution network operators. So we coordinated the program. The distribution network operators have the customer relationship with each of these connecting devices. What we found, because we paid up to I think £2,500 per change. So we were paying the developers to go in there and make the change. And what happened was some companies were spawned just to do that job because they saw there's this huge amount of work to be done. They knew the processes, they knew the paperwork to fill in. And actually what we found was some of these contractors that were doing this as a job, they were going around and finding these sites and selling the services and then making the changes. It's not been easy, and no way are we completed. There is still a little bit of residual vector shift and rock-off loss of mains protection that needs changing. But the volume of INGAO is so low that actually we can sort of just almost ignore it in real time. But it's cost us about £40 million, I think, to do that across the piece. But it's taken us 3 years. I think we've been on that program, and it finishes in September of this year.
Hmm. Quite a burdensome process.
Yes, it has been.
And speaking of vector shift, there's a question below about the angular difference between Scotland and I guess central or southern England. Any idea what that?
Yeah, and I mean, vector shift is an issue, again, because of the loss of mains protection on this embedded generation, the very local voltage disturbance, we were finding that some of the solar and wind, embedded solar and embedded wind farms would trip off the system because their vector shift protection would spot the voltage differential. The bit between Scotland and the south of England, I mean, I'm not sure why, because we've got a very highly integrated, highly meshed system. So actually, you wouldn't see an event in Scotland that you would feel on the south coast because there's so much inertia and so much mass and so many wires between Scotland and the south of England. So I'm not sure what Phil was trying to get at with that question as to what challenge he was trying to find out about.
Okay. Here's an interesting question, I guess, about feedback or questions that you get from other system operators. Are you aware of other TSOs that want to adopt dynamic containment for their system? Is that getting to be a hot topic, or are you the guy out front with the arrow in your back?
So I think all of our networks are so different, aren't they? And different levels of interconnection and different levels of history and market structures or whatever. So I'm not aware that I know people are asking a lot, and when we get on the GPST calls, it is one of those things we have talked about. But we all talk about this trade-off between frequency management and inertia. And obviously, depending on your generation mix, on your market structures and your regulatory structures, will depend on how you approach the solution. So it's not something that I think other TSOs might necessarily be copying, but certainly we're all looking with interest at each other's networks just to see how and where and why are they doing what it is that they're doing.
Okay. Here's a couple of related questions about measurement. Do you think it's necessary to record the real-time instantaneous voltage and current data rather than the RMS values? And what is the coverage of the sensors, PMUs, to help analyze the oscillations and validate the EMT models? And how important is the monitoring of EMT on generator bus bars and controlling feedback loops if they're IBRs?
Wow, that's a lot of questions.
Yeah, maybe one at a time. Is it necessary to record the instantaneous rather than the RMS values?
I think when you look at what happened, as many of you may remember, on August 9th, 2019, yes, August 9th, 2019, we lost 1 million customers here in the UK because the LFDD, low frequency demand disconnection, relays opened on the distribution network because we had a major frequency event. And when we were looking at the data, you need that second by second data or millisecond by millisecond data. And I remember in the incident room sort of investigating what had happened, I remember saying, but that was 20 milliseconds later. That is such a long time because we were down so much in the granular data. So that post-event investigation, you absolutely need that hugely granular detail when you're looking at these types of inverter-based systems to really understand what triggered first and when and which piece of kit was the thing that was contributing or supporting whatever event was happening. That also means, therefore, when you're doing your EMT studies, you need to also be modeling at that sort of level of granularity to really understand how all of these products and devices are all going to interplay with each other and how they perform against each other. So it's a really fascinating and data intensive and time intensive piece of work.
Yeah, for sure. And the next question is related to that. What's the coverage of sensors, PMUs, et cetera, to help analyze oscillations and validate the EMT models? Do you have enough information coming back to really do that, or is that still an area where?
So we have, I mean, the TOs, the transmission owners, have had several PMUs installed for quite some time. With the reactive technologies inertia monitoring, there are many, many more PMUs going in on the system. And that is to get that geographic inertia calculations we spoke earlier. inevitably those PMUs are spread quite wide across the grid system. So I think going forward, we're going to have a wealth of data that perhaps we haven't had quite so much in the past. The EMT models, as I spoke earlier, that is the one area that we're still building that capability and still building the data. But I'm hoping that once we get the EMT models up and running, we can run some simulations and we'll be able to compare what the model is showing versus what the data we can get out of the PMUs and really get that deep understanding. But it's a new area for us. It's new capability that we're having to build. It's new tools, new models. It's a whole new area. It's quite fascinating.
Okay. I'm going to skip down here a bit. Is there any work on revisiting the system under frequency load shedding relay settings that are probably set many years ago and not changed in many systems? They haven't to rethink your UFLS.
Yeah, so there's an initial piece of work which has been completed, because if you remember the media reports around that time on August 9th, we lost a couple of hospitals and an airport and more importantly, the rail network or parts of the rail network. And those types of load should never have been on that first stage of LFDD. Obviously, over time, they apply for connection of the DNO. The DNO gives them a connection, and unfortunately, some of those sort of critical loads were connected to LFDD schemes. So that work has been done. That's all been cleaned up now. So the only load that's on LFDD is low criticality load, so housing estates, whatever. There is more work going on though, because there was a risk that had August 9th happened a couple of hours earlier in the day, certain parts of the LFDD would have had more solar generation behind it, and actually we'd have lost more generation through triggering the LFDD. It was only because it was at 5 o'clock in the evening, the solar output was starting to fall. And actually, when we lost some of those high penetration of solar regions, we were lucky that actually the net effect was either zero or positive because we lost a little bit of demand. So there's a bigger piece of work now working with the distribution network operators, looking at how do they distinguish those loads and how do they put a control on the LFDD, which if it is a net exporter of power onto the system, that if the LFDD event is triggered, the breaker doesn't open, because obviously that's going to exacerbate the problem. So the DNOs are doing a huge amount of work to understand what that looks like. We still need 5% of load at any time available on LFDD for the first stage. So if they are finding they've got many zones where it would be a net positive or net negative, which way you look at it, the loss of generation by tripping LFDD, we still need to, the DNOs still need to ensure that all times they've got 5% available to us through that first stage. So yeah, there's a lot of work going on, and the LFDD, I don't think the person asked is absolutely right. It cannot be a dumb fit once and forget. It's got to be much more smarter than that going forward.
All right. Here's an interesting question from Lena Ramirez, one we haven't really touched on yet, regarding DER. What are the requirements that are needed for the system? How do you see the future with more DER regarding system stability? I know you've got that DER restart project going on in Great Britain also.
Yeah, so
related to that.
I mean, currently in the UK, we've got about 34 gigawatts of distributed energy resources, which means that on a 50 gigawatt system. So during COVID times, we were down to, as a transmission demand, sort of 12 or 13 gigawatts, because the rest of the demand was sort of soaked up by the embedded generation. So it is really having a huge impact on how we think and how we operate the grid system. What we want to do, though, is open it up to markets. So I have a program I run called Regional Development Plans, which is looking at specific regions, looking at the DER within those regions, and creating a sort of a market that solves some of the distribution constraints, but also helps to solve some of the transmission, either voltage or thermal flows, etc. What we're doing, but then on a pathfinder sort of stability and inertia perspective, we are then sort of solving that at a transmission level. So that because in the UK, there's only the GB system operators, only ourselves, that are worried about frequency. Therefore, we think it's right that we allow the DER to connect. We will maximize the use of DER to manage thermal and volts. And Charlie, as you say, we're also looking at how DER can black start the system from the bottom up rather than from the transmission down, which will be interesting to see that develop over the next while. But really, the frequency management, the grid inertia is something that really we manage at a transmission level, and we'll continue to do it in that way.
Just gets everything gets curiouser and curiouser, as they say. One last question, Julian, before we wrap up here. We're just about at the top of the hour. About the study process for interconnection. Going forward, do you see the need to perform EMT-based stability studies as part of the connection request? Is that in the cards?
I think it will be. And some of that will come down to how we define short circuit levels and whether it is left to the developer to solve, or whether it's something that we need to sort of manage and look at and then either buy other devices or do something to network configuration to manage it. Yeah, I think EMT studies are going to have to, in a high IBR penetration area of the grid without any rotating plant, it's got to be part of that future and understanding how that all works. And the thing that hasn't come up on the questions, the thing that worries me the most actually is we can get one IBR stable and it works. It's when you've got a multitude of them all regionally, and how do they all start interacting with each other, and how do you stop them interacting and sort of fighting with each other? And that's the thing that I think worries me most in this whole sort of area of understanding and trying to understand how they work and how the different manufacturers and the different controllers and programming and all that other stuff, how does it all fit together when you've got a live system that's trying to manage a stable network?
Yeah, I think we haven't really paid enough attention to that control system interaction problem, and it's going to be a challenge going forward too with all the black box models that there are for the inverter control. So I guess we have our work cut out for us.
We do.
Plenty to do to keep you employed, Julian.
Yes, all of us.
All of us, right? Okay, so we're a little past the top of the hour. We're going to need to wrap it up. Julian, thanks for a very informative and educational event. I know I learned some new things today, and I hope everyone else did as well. As I mentioned earlier, an email will go out once the video file has been posted, and we'll get the responses to your unanswered questions posted as quickly as possible. There are really a lot of good unanswered questions, and I'm sorry we didn't get to them all, but I think Julian will do his best to get input from his team and get those back to us in the near future. We appreciate everyone's engagement, and if you want to stay engaged, I'd invite you to participate in the February webinars and in the Spring Technical Workshop in March in Tucson, Arizona. Further information on the workshop and all of our webinars can be found on our website at esig.energy under events, and you're all invited to attend. Information on all of the GPST webinars can also be found at globalpst.org. Julian, thanks again for this very timely webinar. Thank all of you for your interest. Look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. Bye now.